Hi everyone, this is George, your IA for Psych 106, and today we're going to be investigating the membrane potential as well as the action potential. So when a neuron is at rest, it's typically between the negative 80 to negative 70 millivolts range. So there's more potassium inside the cell than outside the cell, which means that there's also less sodium ions inside the cell than outside the cell. So there are three factors that contribute to why a resting membrane potential is negative, and that includes diffusion, selective permeability, and electrostatic pressure. When it comes to diffusion, it's just basically that ions want to move from a high concentration to a low concentration until they have an equilibrium. When we talk about selective permeability, this is just how a membrane controls the flow of ions in and outside of the cell. So here we see that this channel is only permeable to potassium ions, so it's only going to allow potassium ions to pass through. We also have to remember that like forces repel and opposite forces attract. So when you have these potassium ions on the right side, they're going to repel each other, so they're going to go back. So this is where we get into electrostatic pressure. So here we can see electrostatic pressure. The potassium ions are concentrated on the right side, and they really don't want to stay there because they want to move to the left side because their like forces make them repel each other. So there's sort of going to be this back and forth movement, and this is essentially what creates electricity, or what is a factor in creating electricity inside a membrane. So now we can see that the equilibrium potential arises from a balance between diffusion rates, selective permeability, and electrostatic pressure, which is really contributing to the generation of an electric potential, which we know as the Nernst potential. So this is just basically explaining that these factors are just contributing to how an ion moves from and across a neuronal membrane, and how selective permeability and the electrochemical gradient plays a huge factor in establishing this. So another important factor in a neuron's resting membrane potential is the sodium-potassium pump. So here we can see that the sodium-potassium pump uses ATP, which is just energy, to pump 3 sodium ions out of the cell and then pump 2 potassium ions back into the cell. And this contributes to helping keep the resting membrane potential at that negative 80 to negative 70 millivolts range. And when I discuss the action potential later, you'll see why this is important. Alright, let's review this one more time. So a resting membrane potential is influenced by factors such as diffusion, selective permeability, and electrostatic pressure. So the combination of these three forces result in the Nernst potential, which then also explains how electricity is generated in our resting cell. Remember, like forces repel, opposites attract. Ions want to move from a higher concentration to a lower concentration, and this back and forth movement helps create electricity in the cell. So at rest, between negative 80 to negative 70 millivolts, that sodium-potassium pump is going to be using energy to pump 3 sodium ions out of the cell and 2 potassium ions into the cell. Alright, let's review this one more time. Which way will the sodium ions move? They're going to move right because it's selectively permeable to sodium only. Now that it's moved towards the right, where will sodium ions flow now? They're going to flow back to the left because like forces repel, because sodium is a positive charge and chloride is a negative charge. And this is creating electrostatic pressure. Now that we know why a neuron's membrane potential is negative and the factors that contribute to it, we can learn about what happens to a neuron when it receives a chemical signal and what factors contribute to an action potential. Alright, take a 3-minute break and get a snack and come back so we can learn more about the action potential. Alright, cool. So last time we discussed that a neuron receives a chemical message, also known as a neurotransmitter. So that neurotransmitter is going to attach to a receptor and then open channels. So a neuron has ligand-gated channels as well as voltage-gated channels. So a ligand is just another word for neurotransmitter. So when a neurotransmitter attaches to a protein binding site or a receptor, it's going to open that channel and allow ions to flow through this. So it's a specific neurotransmitter receptor. So it's like part of a neuron that says, okay, I'm only going to accept serotonin. So it takes serotonin in, and it's like, okay, cool, now I can open that ion channel, okay? So this is an ionotropic receptor/channel. This is a very fast mechanism, and it's only open for a short amount of time. This is a direct effect because it's directly opening when it has the presence of a neurotransmitter. So when it comes to voltage-gated ion channels, these are just ion channels that open when the membrane voltage in the neuron reaches a certain threshold. So we see here that serotonin attached to a ligand-gated channel. It's going to allow sodium ions to flow through, making it more positive. And this voltage-gated channel is only going to open when it's at negative 40 millivolts. So as these sodium ions keep flowing through, it changes to negative 40 millivolts. So here we see that it's almost getting there. It's almost going to be negative 40 millivolts as more sodium ions keep passing through. And once it is negative 40 millivolts, that voltage-gated ion channel is going to open. So in this case, it's a voltage-gated sodium ion channel. So now that it's open and it's received that threshold to open, it's allowing sodium ions to flow through the cell. This is making it a lot more positive now with the combination of the ligand-gated channel and the voltage-gated channel. And this is going to prompt an action potential. Now we also have metabotropic receptors. These are a little bit more complicated. So we know that an ionotropic receptor is just direct passage of ions through the cell. A metabotropic receptor requires a second messenger to send a message to a nearby channel to allow ions to go through. So that's why it's an indirect effect. The neurotransmitter is going to bind to a protein or receptor, and it's going to cause a second messenger reaction, and then it's going to open the ion channel. So here we see serotonin attaches to that G protein. It's going to send those second messengers to a nearby ion channel, and then it's just going to allow the ions to flow through, which is an indirect effect. So this is a slow mechanism, and it's open a lot much longer. So the two most essential neurotransmitters in our body are glutamate and GABA. Without them, you would not be alive. I know that sounds very bleak, but it's true. So glutamate here is attaching to a neuron, and again, that chemical signal is being translated into an electrical signal, and it's going to cause an action potential. And that action potential is actually going to cause an influx of sodium ions to be released in the postsynaptic neuron here on the right. And it released so much that it actually made the cell so positive that it generated an action potential. So that's why it's excitatory. Glutamate really just wants an action potential to happen. It wants something to keep happening. Okay, and side note here, I drew that circle neuron in the presynaptic. I meant to draw it on the postsynaptic. So imagine that's on the right. So when it comes to GABA, it's an inhibitory neurotransmitter. So GABA here is released and it's being sent to a neuron. That chemical signal is being translated into an electrical signal. But remember, this is a presynaptic neuron, so an action potential is still going to be generated. So as it does generate and then goes to the axon terminal, it's actually going to release chloride ions. Chloride ions are negative, and they are going to make the postsynaptic neuron here on the right a lot more negative, so it's hyperpolarizing the neuron. It's preventing it from having an action potential because the cell is so negative. So now we can see that the resting membrane potential of the postsynaptic neuron is at negative 70 millivolts. But now with the influx of chloride ions from the presynaptic neuron that was triggered by GABA, it's going to make the postsynaptic neuron go to negative 80 millivolts. And that's a lot more negative than it was before. So it's preventing an action potential from happening. Okay, so let's review this one more time. Glutamate is an excitatory neurotransmitter, and it's going to cause an influx of sodium ions in the postsynaptic neuron, which helps generate an action potential, which is why it is an EPSP. GABA is an inhibitory neurotransmitter, and it's going to cause an influx of chloride ions in the postsynaptic neuron, which makes it more negative and less likely to start an action potential, which is why it is an IPSP. Okay, so now we can finally focus on the phases of the action potential. So here at phase 1, we have our resting membrane potential. Our cell is negative, it's at negative 70 millivolts, and it's not doing anything. There's just more potassium inside than outside the cell, and there's more sodium ions outside the cell than inside the cell. Alright, so in our depolarization phase, we have our neuron receiving some chemical input or message that's triggering voltage-gated sodium ion channels to open. So as more sodium ions enter the cell, it's becoming a lot more positive. And that energy is being summated at the axon hillock to reach a threshold and initiate an action potential. So in this phase, our potassium ion channels are also closed, and the cell is becoming more positive because it's in the phases of an action potential. So now in our repolarization phase, our voltage-gated sodium ion channels are actually closed. And our potassium ion channels are now opening back up, and a lot of potassium ions are exiting the cell. So when you have a lot of positive ions, in this case positive potassium ions exiting the cell, it's going to make it very hyperpolarized. Now it's becoming a lot more negative than it was before, and that's when we get to the undershoot. So now potassium and sodium ion channels are closed, and the cell is a lot more negative than it was before because it's trying to get back to that negative state. So it usually goes down to around negative 90 millivolts, and then our sodium potassium pump, which we discussed earlier, is going to work to pump 2 potassium back in and 3 sodium ions back out to try to get back to that resting membrane potential, which was about negative 70 millivolts. Cool, so now we're back at our resting membrane potential. So we're back at negative 70 millivolts, and now the neuron can have another action potential if it's prompted. Okay, so let's review this one more time. So at phase 1, we have more sodium ions outside the cell than inside the cell. Just ignore that there's 2 inside and outside. It should be like 3 inside and 2 outside. And we have more potassium ions inside the cell than outside the cell. And it's at negative 70 millivolts. In phase 2, we have our depolarization phase. Remember, our voltage-gated ion channels for sodium are open now, allowing more sodium to enter the cell, and our potassium ion channels are actually closed at this phase. So now it's reaching like negative 50 millivolts, so now an action potential has started. In phase 3, we have our repolarization phase. So voltage-gated sodium ion channels are closed. Now our potassium ion channels are back, and they're going to cause more potassium ions to exit the cell, making it a lot more hyperpolarized, a lot more negative. Now we move back to our 4th phase, which is our undershoot. So now a lot of potassium ions have left the cell, and it's very negative. It's around like negative 90 millivolts. And in this phase, our potassium ion channels are closed, our sodium channels are closed, and now our sodium potassium pump is going to be used to pump 2 potassium ions into the cell and 3 sodium ions out of the cell, and go back to that resting membrane potential that we were at phase 1. Okay, so that was a lot of information in today's video, and I just want to say thank you so much for sticking around and listening, and I believe in you guys. Let's test our knowledge one more time. We're going to go over everything that we discussed in the beginning of the video. So pause this video and then come back when you're ready to answer. So what factors contribute to a neuron's resting membrane potential? Remember, that's diffusion, selective permeability, and electrostatic pressure. Okay, so for the second question, I'm going to walk you guys through it because I didn't really discuss it in that much detail, but it's just basically selective permeability. So our neuron is at negative 80 millivolts, it's at rest, and the equilibrium potential of potassium is at negative 75 millivolts. So what is the net flow of direction for potassium? So remember, our neuron wants to be in equilibrium with the equilibrium potential of an ion. In this case, our ion is potassium, and the equilibrium potential for potassium is negative 75 millivolts. So because potassium is a positive ion, it's going to flow inside the cell to make the new membrane potential negative 75 millivolts. Alright, so a ligand-gated channel is activated in the presence of a neurotransmitter. Meanwhile, a voltage-gated channel is activated when a membrane reaches to a certain threshold that allows ions to pass through. Alright, glutamate is excitatory and GABA is inhibitory. Glutamate allows for sodium ions to enter the cell and start an action potential. Meanwhile, GABA allows for chloride ions to enter the cell and prevent or stop an action potential from happening in the postsynaptic neuron. So in the depolarization phase, sodium ion channels are opening, causing sodium to enter the cell and make the neuron less negative or more positive. In the repolarization phase, sodium ion channels are closed and potassium ions are exiting the cell and causing the membrane to be more negative, aka hyperpolarized. So in the undershoot phase, potassium channels as well as sodium channels are closed, and the sodium potassium pump works to restore the resting membrane potential. Alright, thank you so much guys for sticking around in this video. I really hope that you guys found this video helpful. I will be posting this on Canvas, but best of luck on your midterm. You guys got this. I believe in all of you, and have a great day. Thank you.